Chapter 11, Number 19. A torque of 13 Newton meters is applied to a rectangular object shown in the figure. The torque can act about any of the XY axis, the Y axis, or the Z axis, each of which pass through the origin and the Z points out of the page. In which case does the object experience the greatest angular acceleration? I can explain. And then it just says calculate them, so that's how we're going to answer the question, but I guess we can have some instinct ahead of time. So we're going to come back to the idea that the torque is related to the angular acceleration via the moment of inertia, tau equals I alpha, which remember is the equivalent of F equals ma. So to get the greatest angular acceleration, we're going to want the least moment of inertia. And then we want to remember additionally that the moment of inertia is always like some number times the mass times the distance squared, where the distance is to the axis. So for instance, if we talk about the rotating around the x-axis, so something spinning around that, which would mean that kind of this coming out of the page at us and looping around, then we would have that in that case, this one and this one would not contribute, and we would just have 7 kilograms that's half a meter away. All right, so our moment of inertia would be 3 kilograms times half a meter quantity squared plus 4 kilograms times half a meter quantity squared, which turns out to be 1.75 kilogram meter squared. And if we're rotating around the y-axis, so we're spinning out of the page sort of that way, then we see that neither this nor this contribute, and instead we would have 4 kilogram times 0.7 meters quantity squared plus 1.2 kilograms times 0.7 meters quantity squared. This is 2.548 kilogram meter squared. And then finally, if we're rotating around the z-axis, which is this thing, and I can't really draw it, but it means the whole shape is rotating in the plane, then this one doesn't contribute. Notice it hasn't contributed to any of them because it's at the origin, so any axis through it won't contribute at all. And instead we get 3 kilograms times 0.5 meters squared, that's this one, plus 1.2 kilograms times 0.7 meters quantity squared, that's this one, and then plus 4 kilograms, but then we need to know the perpendicular distance to the axis, which is that distance, and that's going to be a little bit annoying, so but we need it squared, and that's easy because that is a hypotenuse of a right triangle, so the square of that distance is going to be the sum of the square of this distance plus the sum of the square of this distance, or it's going to be 0.7 meters squared plus 0.5 meters squared. That's a little bit more grungy, but when we plug it in, we get 4.298 kilogram meter per second square. And then all we need to do is go back to this formula to figure out what the actual accelerations would be. So our first thing that we can see is that since the angular acceleration is inverse to the moment of inertia, we see that the greatest angular acceleration is around the x-axis, and then the next will be around the y-axis, and then finally it'll be slowest around the z-axis. So that's sort of the answer to part A. But now we can just get those numbers and see that that's what comes out. So in each case, we take the 13 Newton meters and divide by the angular acceleration, or by the moment of inertia that we got in each case, so as to produce the angular accelerations. And we see, as predicted, that x comes out the highest and z comes out the least. Maybe a real quick check on the side, reality check on the units. We have Newton meters over kilogram meter square, and a Newton meter is a kilogram meter per second squared times meter over kilogram meter square. And so we get something per second squared, and we know that the radians don't respect dimensional analysis, so they kind of just pop in here and say it's really radians per second square.